Okay, so here we're going to solve problem 3, which was the full problem with the core of cells with Michaelis-Menten kinetics and the shell of alginate with no consumption. And we're going to solve this numerically using the shooting method and using Runge-Kutta fourth order. So you saw in the setting up of this problem 3 that we wound up with two ordinary differential equations expressed here. This first differential equation expresses the what I'm calling the interior solution, u sub I. So that's the second derivative of u sub I with respect to rho, minus this consumption term, which is nu u sub I over kappa plus u sub I rho to the minus 1, and that's equal to 0. And then the second problem is the exterior problem, which I'm categorizing as u sub E for external, and that's just simply the second derivative of u sub E with respect to rho is equal to 0. So with these two ordinary differential equations, each one being second order, we need to have four boundary conditions. Our first boundary condition is that the interior problem at rho equals 0 is equal to 0, and the exterior solution at rho equals 1 is equal to 1. So remember, our rho is our dimensionless expression of distance, and we have that being valid for the range of 0 to 1. Our third boundary condition is that at the interface, and because our interface is dimensionless, our interface is R1 over R2, where R1 is the radius of the interior cell, and R2 is the radius of the exterior. So the interior solution at rho is equal to R1 over R2 is equal to the exterior solution at rho is equal to R1 over R2. So at the interface, the two solutions have to be equal. And those can also be expressed as C1 over C2, because remember we had a dimensionless expression for concentration in which we divided the entire interior by this C2, which is our exterior concentration that we're holding constant. And now our third boundary condition, has to do with the flux of matter. Basically, we're saying that because we're solving the steady state solution, the flux across the interface, both coming from the left and coming from the right, that flux has to be equal. And we know from Fick's first law that the flux is expressed as the diffusion coefficient times the derivative of the concentration, and when we went through our derivation, that gave us di, the interior diffusion coefficient, times the derivative of ui with respect to rho at rho equals R1 over R2 is equal to d sub E for exterior times du E d rho at rho equals R1 over R2. So this is the problem we're going to solve, and we're going to solve it numerically. So just as we solved the first part, which was just solving for the cells, we're going to take the second order differential equation and transform it into a first order differential equation by changing the variables from u to v. So we're going to say that u sub I is equal to v1 sub I, and the derivative of u sub I with respect to rho is equal to v2 sub I. And then, because we want to solve this by Runge-Kutta, we have to be solving a initial value problem, not a boundary value problem, which means that we have to re-express our boundaries in terms of initial conditions. And the way we're going to do that is we're going to define v1 sub I0 equal to 0, and that just came because u at 0 is equal to 0. And then this derivative, we don't know the value. So we're going to guess some value, and this is beta, and that's our shooting parameter. So we're going to be using the shooting parameter method, and we're going to adjust this until our solution comes out self-consistent and gives us the boundary conditions that we originally wanted. So we get the boundaries at the exterior of the problem. So these are now our initial conditions, and then we can transform these into all v parameters. So dv1i by rho, or d rho, is equal to v2i, and then that's just by definition actually, and then the derivative of v2i with respect to rho is equal to our Michaelis-Menten parameters, in which in place of the u we put in our v1i. And we're solving this problem over 0 less than rho less than r1 over r2, right? This is the interior problem, so we're limiting our solution to this range. So we want to solve this by Runge-Kutta, and this gives us a way to express our problem as a linear system of ordinary differential equations with an f and a g function and initial conditions. And if you remember from when we solved the Runge-Kutta solution for the cells only, we have a kind of an issue, because at rho equals 0, our g function gives us this, which taking our rho up and into the problem, we get nu v1i rho is equal to kappa rho plus v1i. And we want to look at this at rho equals 0. Well, rho equals 0 means we get a 0 there, we get a 0 there, and v1i is also 0. So we get 0 divided by 0 plus 0 is equal to 0. And taking the limit and getting a solution 0 of 0 means that we can use L'Hopital's rule. And L'Hopital's rule says that this limit, which is indeterminate, is then found by taking the limit in which we take the derivative of both the top and the bottom. And doing that, we get this solution in which we have nu. Here we have v1i rho at rho equals 0, which is 0. Here we get rho times this derivative, which is this derivative of v1i prime is a finite value. It's not infinite, which means that the rho equals 0 in front of it makes this go to 0. This kappa is just some finite value, because we took the derivative and that got rid of the rho. And this v1 prime rho is again just a finite value, which means we have a finite value divided by 0, giving us 0. Which means that in the limit that rho goes to 0, g sub I at rho v1i, v2i is equal to 0. And we're going to use that in the first iteration of our Runge-Kutta. And that's, again, solving from 0 less than rho less than r1 over r2. And after we solve this, so we're going to start at the interior and we're going to solve up to the edge, we're going to wind up with v1i at r1 over r2 is equal to u1i over r1 over r2. And v2i at r1 over r2 is equal to the derivative of ui with respect to rho at rho is equal to r1 over r2. So basically I'm just saying what comes out of the problem after we solve the interior with Runge-Kutta fourth order. And these are important because these are going to be the starting point for solving the exterior solution. So the exterior problem is now defined for rho ranging from r1 over r2 less than rho less than 1. And again, we take our u sub e ordinary differential equation and we re-express that in terms of two new variables, a v1e and a v2e, where v1e is just ue and v2e is the derivative of du de with respect to rho. Going to our boundary conditions, I should say our initial conditions. Our first initial condition is that on the left-hand side of our problem, u1e at r1 over r2 is equal to u1i at r1 over r2, which is ui over r1 over r2. And that is one of the outputs coming from our solution to the interior. Our second initial condition is that u2e at r1 over r2 is equal to u2i over r1 over r2 times the ratio of di over de. And this problem, that setup, comes from our boundary condition here on page 1, in which we say in which we say that the flux on the left and the right hand side of the interface have to be equal. So that ratio of di to de becomes important. So we get du sub I over d rho at rho is equal to r1 over r2 di over de. And this is the problem we're setting up. We can now rewrite our differential equations all in terms of the u variables. So first one by definition is this. And then the second one is this, which is 0. So that's just a re-expression of our differential equation. And that gives us this set of equations, which now have a f sub e and a g sub e, and initial conditions with known values coming from the interior of the problem. And this is now something we can simply solve by Runge-Kutta fourth order. So we're going to solve this problem starting with the interior, making an initial guess at what the slope is at rho equals 0, solving through the interior to the interface, solving from the interface to the exterior, and we're going to look at what the final value is at the exterior, and we want to make sure that whatever we pick for this beta is going to give us a is going to satisfy that u sub e at rho equals 1 is equal to 1, our final boundary condition. So this is how we're going to use the shooting parameter to make sure we get to the right solutions.